Here's a couple of examples of finding the volume of a region of revolution where you're revolving around an offset axis, not just the x or y axis, and that tends to get to a level of complexity that confuses people. These are a couple of problems that I wanted to make sure that we understood. Didn't have time for in class. And so here's the region bounded by x equals y squared. That's otherwise known as y equals root x. That might be useful. We'll see if we need that or not. Just rewrite it as y equals root x. We'll see. And x equals 1, except, well, wait a minute. If x equals y squared, it's not just y equals root x. It will be plus or minus. That would be annoying to have to deal with, because it's really everything down here. And then x equals 1 is this line. Okay. Now, as I've been doing in class, what I encourage people to do is to save a copy of the 2D picture, even though you want to draw the 3D picture as well, because the 2D picture has most of the information in it. So what are we going to do? We're going to take this region between these curves, and we're going to revolve it around the line x equals 1. So the way you draw that is you copy it over and then draw some circles. One important comment is that doesn't mean that there's like two parts to this. It's just that when you look at something that's 3D and you put it into a plane, you're necessarily just slicing one slice through it. Well, you do get two halves of that thing, but it's really a whole 360 degrees of revolution, which is the important thing. And that's what these circles are supposed to represent. Now, the nice thing about this problem is that it is an offset axis, but it's not a washer problem. It's not something where there's a hole in the middle. The cross-sections here are just disks, and that does make things somewhat simpler. Another way to say that is we're taking a strip, the kind of strip we would use if we wanted to find the area of this region, and we're revolving it around that axis to make this a thin disk shape. So that's most of our picture. The other picture I always encourage people to draw is take one of these slices, whatever it is. It's often a disk or a washer, but sometimes it's something more complicated. And just draw a picture without a lot of complexity or anything. A picture of just one of those representative slices. They're going to be different sizes. I'm not trying to suggest they're all the same size, but I want to get a qualitative picture, and I want to have a place to put this, which is the radius of that guy. The radius there also lives here, and it also lives here. That radius, you could also put it over here as well. And notice that's exactly the length of that strip. Now, that's because it's glued on to the axis of revolution. There's no gap. And when there's a gap in a washer kind of situation, a hole in the middle, then that's a little more complicated. Okay, so that's a pretty good picture. And so the way I lay it out, let's go to another sheet, and we'll come back to the picture. The whole is the sum of its parts, and each part is a cross-sectional area times the thickness. Well, what's the thickness? It's going to be a change in the y variable, because these strips are labeled by the different y variables that correspond to the different heights. And so that's telling us that the y variable is going to be our variable of integration. And the other thing that tells us that is that the thickness of that thing is dy. And so it's going to be the area of one of these guys, in other words, one of these slices that's in here at whatever level, times the thickness dy. Now, it's not going to be a pi big R squared minus pi little r squared thing here. It's not a washer, it's just a disk, and so that's going to be pi r squared dy. But we need to get that in terms of y, and that's where these three pictures are really useful. The pi r squared comes from just looking at this picture. But where does that r fit into the big picture? It fits into here. Well, can we put that into a simpler picture that lets us figure out where that came from in the first place? Yes, it's the r that's right here. And that's the length of a segment along a horizontal line. So that's a difference of x values. It's the difference between the x value of the right-hand side, which happens to be just 1, because it's a very simple flat edge here, and the x value here. And that's where this is really nice. And we do get a break. We don't have to solve. We don't have to do plus or minus root x. It's just going to be the x value that corresponds to a given y is y squared, because this is the curve x equals y squared. If I tell you I'm looking at slice y, which is what this is telling us, that y is the controlling variable for the integral, I need to tell you, in terms of that variable, where is this location along the x-axis. So that's exactly what this tells us, x equals y squared. So we're going to get that radius being 1 minus y squared and then squared dy. Okay, and here's a situation. It's very different from the washer situation. In the washer, it's you square first and then subtract. So I'm going to compare, and we'll do another example in a minute. Compare to pi big R squared minus pi little r squared. There, you square first and then subtract. That's because you're taking an area minus a smaller area, this kind of picture. That's not what we're doing here. What we're doing here is we're taking the difference of 2 points on a number line to find a distance, getting one single radius that goes in as the radius here, and then just squaring that, and that's it, and times pi, of course. And so it's subtract first and then square when you have an offset axis and no washer kind of situations. In the more complicated situations, like some things in class, and maybe I think maybe the next example, you do both. And that can be a little complicated. Okay, and so that's going to be something we can calculate. Oh yeah, and this is usually where I put the limits in. What are all the different y values? Well, that's where these intersections are really crucial. Where does x equals y squared intersect x equals 1? Well, y is going to be plus or minus 1. So we did have to combine these two things and do a tiny bit of algebra, as usual. If we wanted to, we could use a little symmetry and notice that it's just twice the top half and go twice from 0 to 1. But that's not super important. Okay. And that's going to be, I might as well finish that off. Well, so let me do that. So 2 times pi times 0 to 1 of 1 minus 2y squared plus y fourth. This is usually the relatively easy part, now that we're kind of used to anti-differentiating and things like that. And the fact that we have a 0 now is kind of nice, and it avoids some annoying things with minus signs. So that's the value we get out of the little symmetry idea. So 1 minus 2/3 plus 1. Actually, yeah, I do want to go to the final answer because I always want to recommend that we check the answer for reasonableness. So that's a third plus a fifth, and so that's 5/15 plus 3/15 times 2 pi. So that's 8 pi, yeah, 16 pi over 15. About 3, a little more than 3. And if you go back to this, this looks kind of like a sphere. It's not a sphere. It's pointed. It's got a sort of sharp corner at the top and the bottom, a little bit. But it's kind of spherical. And it's if it were a sphere, the radius would be basically 1. And so that'd be 4/3 pi r cubed, or 4/3 pi. And so this is a little bit less. Instead, 16/15 is a little bit more than 1, but not as big as 4/3. So it's a little bit less than a sphere, the same radius. So that should be correct. That's probably pretty good. Remember, never give a negative answer for this unless you say, boy, I don't know what's going on, but I don't know how to fix it, but I know it's not supposed to be negative. Okay, I'll do one more example in a different video.